So, good morning, pets community. So, the presentation was enough. I'm Samuele Casarin from Foscari University of Venice. I am at the School for Advanced Studies, Lucca. And in this presentation, we compare two representative techniques for web tracking detection, and we're going from syntactic matching to taint tracking and back. So let's start from the problem, stateful tracking. This is the traditional form of web tracking. Essentially, it works in two steps. First, the website sets some identifiers in the client-side storage, in the browser storage, and subsequently, in subsequent visits, the identifiers are read from storage and sent to third-party trackers, thus identifying the user. Now, as you may know, this is a very prevalent privacy problem, and there were many techniques that were proposed in order to detect this phenomena. It is not enough to just compare directly the client-side storage network request in order to detect this phenomena, because identifiers possibly may be transformed before transmission. For example, they can be base64 encoded or encoded. So what we do, however, the problem is that how well effectively do these techniques work? That's what we do. We compare two techniques, two representative techniques. One based on heuristics, which is syntactic matching, and a more principled one, which is taint tracking. So, and to do this, we construct a data set of tracking requests, meaning requests which sends identifiers to third-party trackers. From the trunk top 10K sites, we perform an empirical comparison in which we explore the strengths and the weaknesses of these techniques in terms of false positives and false negatives. And finally, we evaluated the implications for web privacy analysis, and moreover, we propose some methodologies to get the best from these techniques. So let's start from our protagonists. The first technique is syntactic matching, which detects occurrences of identifiers in storage within HTTP requests. So, as it is based on heuristics, it is easy to implement, but it cannot handle too complex transformations, leading to false negatives. And moreover, it cannot guarantee that matched values are effectively read from storage, leading to false positives. We consider a representative implementation of syntactic matching, which is a union and generalization of existing heuristics from the literature. It works in two steps. First, starting from identifiers detected within the client-side storage, we try to recursively apply some transformations in order to generate other identifiers. And then we try to look for those identifiers within the parsed components of network requests, such as query parameters, like in this example. In this case, that request to tracker.com leads to a syntactic match, and it is a tracking request. The other technique that we evaluate is taint tracking. This is a more principled approach that tracks information flows from storage sources, for example, document.cookie, JavaScript sources, to network sinks, for example, the well-common sinks fetch or XHR. So, as it is more principled, it captures information flows throughout JavaScript execution with more precision. However, it is very hard to implement, often requiring some browser modifications. And also, since it tracks all values coming from client-side storage, intermediate transformations may lead to false positives So in our implementation, for our implementation, we take a state-of-the-art engine for taint tracking, which is called Foxhound, which is a modified version of Firefox enhanced with taint tracking, that we further modified by putting taint granularity at byte level. So as you may see in this example, here we have an information flow from the document.cookie source, applying some transformations that preserve the tracking potential of the read identifiers. And finally, the identifier, transform identifier, is sent to the trackers by means of a fetch, which is the sink, the network sink. You can also see at lines 5 and 6 that thanks to byte level taint tracking, we can recognize those information flows that do not preserve the tracking potentials, like in this example, we have a single character read from identifier in storage, but that is repeated 8 times, and thus it has not enough entropy to allow a unique identification. So now, to compare these two techniques, we employ the following pipeline, starting from a site list of 10K sites. We first perform a first visit in order to pre-populate the client-side storage, and another independent visit to detect identifiers according to well-known heuristics from literature. Then we concurrently collect the network request and taint flows at the same time. And then we compute the tracking requests by means of processing HTTP requests for the syntactic matching and taint flows for taint tracking. And finally, we validate the request to ensure that they are not spurious matches, okay? To ensure that they are true positive. Let's put the lens on this last step, since it is not, it is intuitively a bit difficult, okay? I will give you a high-level idea of how it works. So we wanted to confirm or refute tracking request detected by syntactic matching. So let's start from a syntactic match, okay? So we have a cookie and a tracking request that we wanted to validate. What we do is we transform the cookie in storage by applying some minimal and minimal invasive transformations that do not break the underlying transformations. And we modify and generate the modified underlying identifier. We call it a canary. Then, with this modified version of the client storage, we rerun the website with another visit and rerun syntactic matching. And if we find that a canary appears in a matching request, like the one that we see highlighted in yellow, then we confirm the original request as a true positive. Now that we have all the ingredients, let's look at some findings. Talking about false positives and false negatives, we find that the taint tracking is more precise than syntactic matching because we find that 27 to 30% of tracking requests found exclusively by syntactic matching are false positives. And all tracking requests, while all tracking requests found exclusively by taint tracking are true positives. Then we find that, talking about false negatives, we find that syntactic matching misses 17% of tracking requests because of the missing visibility of the JavaScript logic and unsupported transformations by all the considered heuristics. And also Taint tracking misses 28 to 29% of tracking requests due to both implementation limitations. For example, Foxhound does not support Taint tracking over data types different from strings, but also more conceptual limitations, such because, for example, Taint tracking does not track Taint flows through over HTTP redirects. How to improve this data? So we find that the validation algorithm improves the precision of syntactic matching, and this allows you to define a more precise variant of syntactic matching, which is the one obtained by considering just those tracking requests confirmed by the validation algorithm. But still, this algorithm has no visibility of the JavaScript logic. So there is an alternative, which is merging tracking requests detected by this variant and Taint tracking, which achieves significant gain over the confirmed variant and Taint tracking. So in conclusion, we find that Taint tracking is more precise than syntactic matching. However, syntactic matching is still predominant in literature due to its simplicity. Unfortunately, state-of-the-art engines for Taint tracking, such as Foxhound, still suffer from many false negatives. The best solution that we find is hybrid, meaning combining the confirmed variant of syntactic matching and Taint tracking. As future work, we plan to extend the comparison to techniques for detection based on machine learning and contribute to Foxhound to further enhance its coverage. And thank you for your attention.